Yeah, thanks for having me. Sergey sent me the seminar schedule for this week of PGP, and I appreciate it. Despite you have apparently a seminar every day, at least you all made it to come here and want to listen to me. May I just ask a quick question? Who knows what synchrotron microtomography is? Okay, so just to give me an indication of how much time I have to spend on explaining it. Well, it's a big title in a sense, but I want to start very grounded. When I finished my PhD in Berlin, I decided it was time to leave the continent for a while, and I went to Perth. And Klaus is a numerical modeler, and as soon as he had kind of realized what he had gotten himself into by hiring a geologist, he sent me out into the field again, to the desert, and there was like in Central Australia, where I took this photograph here, and what you can see here for the non-experts who have not spotted that at first sight is a shear zone in a piece of rock. It's a granitoid gneiss, in fact, which has some background. You can very nicely see how the foliation is deflected here, and these shear zones are quite interesting for us under some circumstances, because upon the condition that the rock, as it was deformed, actually rheologically softened, we can use the shear zone margins to learn more about how that strain localization process actually happened in that rock. I want to illustrate that with these two figures here. I collected this hand specimen here, which covered that margin of the shear zone where the foliation is deflected, and here's the shear zone center. And these are two micrographs taken with a scanning electron microscope, obviously, and you can see how fundamentally different the two microfabrics are. Here you can see a microfabric which is kind of a protomagnetic microfabric, K-feldspar, plagioclase, and unfortunately we cannot see that very clearly, but there's like large, very prominent monomineralic quartz ribbon bands sitting in here. And if we look at a micrograph from the center of the shear zone, then we can see that we still have these K-feldspars here. We don't have any plagioclase anymore, and we have this kind of polyphase mineral mixtures. And for the microstructural geologist, this picture tells us that this rock has deformed very efficiently by a process, probably most dominantly by a process called viscous grain boundary sliding. So we can see this strain gradient here. What we also can learn is from this strain gradient how this fabric has been transformed into this fabric. And essentially what was involved in that transformation was that we had to break up this rheologically dominant monomineralic quartz bands, of which we only see fragments left, or like traces left in here. And the other thing is, obviously, there's a few metamorphic processes going on. It's nothing too complicated. And it's, in fact, Florian and Robin have kind of linked these metamorphic processes in what they call cyclic reactions. Is a bit of an unfortunate term. If you ask me, what's happening there is the plagioclase is decaying, and we can see how that happens. It's being dissolved here. This is again a scanning electron micrograph taken from a split sample, and we can see that the sodium is actually reused in flame lamellae in K-feldspar, which releases potassium, which then is used together with the calcium to form this polyphase mineral mixture. And the polyphase mineral mixture forms in a way that secondary minerals actually nucleate within this monomineralic quartz ribbon bands, kind of dispersing this rheologically very dominant element. The important takeaway from this is that the whole process involved mass transfer along grain boundaries over distances that are substantially larger than individual grain diameters, which means that solid state diffusion or dry diffusion along grain boundaries was far too slow to achieve that in a geologically reasonable time. So the mass transfer definitely involved some fluid. Now, thinking about fluids in rocks, obviously any fluid in a rock has to reside in a pore. I mean, don't have to tell you that. The same is of course true for metamorphic rocks. The thing is with metamorphic porosity that metamorphic pores are highly dynamic. They're obviously continuously evolving and adapting to changes in pressure, temperature, and the rock composition. That was known a long time ago, and also was known that at any point during a metamorphic evolution of a rock, there may be one or more processes producing metamorphic pores as a consequence of these adaptations. And We also know, or it's pretty easy to reason that not all metamorphic pores contribute to permeability, so to the ability of the rock to actually transfer fluid. However, quite intuitively logic is that a dynamically evolving permeability controls fluid-rock interaction. And there we are, actually, because fluid-rock interaction, obviously one of the key processes that we're interested in hard rock geology. And to understand that and to be able to quantify that properly, like on a multi-time and spatial scale, we need to understand the metamorphic permeability a bit better. And that has motivated probably thousands of studies. Many of them were limited by the possibilities these researchers had to assess these processes that they were studying. So what they could do, and what is still being done, is either do an experiment where we measure kind of a bulk property, any change in say how much fluid goes in, how much fluid goes out, and so on, or the strength of a particular rock body. However, we characterize the process on kind of a continuum scale. We don't look at what's actually happening. The only way that we can do it is by a post-mortem assessment. So we take the sample out of an experimental array, cut it open, make a scene section, interpret what happened before, and the same is true for any piece of rock that we collect in the field. Obviously, we try to kind of learn what might have happened or most likely happened. Synchrotron X-ray tomography, and synchrotron is in brackets here because X-ray tomography is one of a series of novel techniques that allows us to study these processes while they're happening, technically, at least in a non-destructive fashion. Now, what is synchrotron X-ray tomography? Synchrotron X-ray tomography is based on radiography, and I found this when I prepared this presentation. I found this artist Nick Vesey, who's scanned all kinds of objects from humans, obviously, to plants to jumbo jets. And this Mini Cooper shows you what a radiograph is. Obviously, he placed this Mini Cooper between an X-ray source and an X-ray detector, and the signal that we see is essentially how many of the photons that went into the Mini Cooper made it to the detector on the other side. So the darker the signal is, and that is correlated to the X-ray attenuation, which is related to the density of a material. Like in the engine part here, for example, the fewer photons actually made it to the other side. So that is a radiograph. We do the same thing, or synchrotron tomography, or X-ray tomography in general, is based on the same principle. We take a series of radiographs, and this is a piece of Berea sandstone, and what is just seen is radiographs that were taken from different angles. So essentially what we did was we rotated the Berea sandstone and took a radiograph after each rotation. Now, the way how synchrotron X-ray tomography works and how we get from this to a three-dimensional model of that piece of Berea sandstone works roughly, and it's very crudely, very much simplified, like this. Think of this is our detector here, which has a resolution of 2048 by 2048 pixels. Think of the signal that is detected along one line of these pixels, schematically shown here. So now we just show essentially on top of this plane. We see the X-rays, the photons coming in here, we see our object, and we record a signal which is correlating to the amount of photons that have been absorbed on their way through that object. This is kind of the signal that is being detected at any particular orientation. If we rotate the object, and the rotation angle is actually shown here now, and stack them, all of these signals on top of each other, and now this is only for one plane, then we get what is called a sinogram. And from these sinograms, through a process called filtered back projection, we can reconstruct what the object looked like, or looks like. It's a non-destructive way. So these are only just these various signals taken from different orientations, kind of back projected, and then what's left in the end is this thing. The good thing, so if we do that for all 2048 slices, then we can reconstruct the three-dimensional shape of that sample. I apologize for the dark appearance here. This is a piece of tile which sits on a piece of tile mortar, and this is a commercial project that I was involved in recently. And what you can very nicely see here is obviously the tile, which is some ceramic. You can see quartz in here, and what you can also very nicely see is porosity, because porosity, empty or gas-filled space or fluid-filled space, attenuates much less of the photons than any solid matter does. So we use that technique in our question with this hand specimen that we collected earlier on, and I want to come back to that question now: the fluid transfer and essentially the transfer of the chemical components. And we pictured the porosity in the shear zone center, and that's what you see here. This is a tomographic data set. The gray values correspond to X-ray attenuation. You see various minerals in here. And what I highlighted in red are all the pores in there. And, we can debate whether this is really synchromatic porosity or not. I have a few good reasons to argue that it is synchromatic porosity that we see. The important thing is really that we can very nicely visualize the pores that are in there. And we see that they actually form pore sheets subparallel to the malonitic foliation, this very fine-grained ultramalonite. If we split that sample open and look at it again in the scanning electron micrograph, and these are now 200 nanometer scale bus, very high resolution, and we can see some of these pores. They're actually grain boundary cavities, and we find that these incisions kind of indicate us that material dissolution was heavily involved in their creation. There's another process that we claim was involved in their creation, that is a process called creep cavitation, and we know that process from metals and ceramics. They deform by this way, or this process is active during the deformation of metals under certain conditions. The underlying assumption is that you have like a very fine polygrain, polyphase mineral mixture, and the grains are sliding past each other during viscous grain boundary sliding, that dominant deformation mechanisms. However, of course, they cannot all slide in the same directions with the same velocity, so there will inevitably be incompatibilities and gaps opening. That is a well-known process. The only kind of extension that we did to this was that, that we said, well, we have experimental evidence that these pores most likely could communicate with each other through grain boundary fluids, fluid-decorated grain boundaries, and as they dynamically, synkinematically change their shape, some open, others close, there will be pore fluid pressure gradients between neighboring pores, and so fluid will actually be pumped amongst them. And that fluid is loaded with chemical components, and at the appropriate sites, material will be dissolved or will be dumped. So we will have, here we have a mechanism for how we can actually disperse these monomineralic quartz ribbon bands. We found another very good example, this is unpublished data now, for how that process could operate or how important it could be. This is also another very fine-grained ultramalonite, also from Central Australia, the same kind of tectonic system here. We have a banded ultramalonite here. It's also a granitic composition, more or less, K-feldspar layers here. We have the intermediate grays, plagioclase, and we have the dark gray layers are actually quartz layers. And even in the scanning electron microscope, you can see that in these rocks there are pores, and they're kind of confined to the quartz layers. That is quite an interesting thing, because if you think about it in the context of shear zones being fluid transmitters or inhibitors, what this would mean, if this was really synchromatic porosity, it would mean that the fluid could only propagate in a particular plane. It could not propagate transversely here. This is a kind of a special piece of tomography that I'm going to show you. This is a nanotomographic data set, and the diameter of this cylinder here, which we extracted in situ, was a hell of a challenge. It's only 20 microns, so it's a very narrow field of view, but the advantage of that nanotomography technique is that it has a very high resolution, so we can have a voxel size of in the order of 35 nanometers. And indeed, if you look at this movie, then we see, which is it's not the exact position here, it's a comparable position, but we see that it's essentially one interconnected pore in a quartz layer here. So we have a safe kind of indication to assume that really there was fluid movement possible if that is like what was a synchromatic pore configuration. This is work in progress. We're still analyzing this. It's not that trivial due to the data quality and stuff. What I've shown you now is essentially two mechanisms to produce porosity, metamorphic porosity. The one is dissolution, we all know that. The other one is creep cavitation, which we claim is also active in natural shear systems. If you think about what other mechanisms would likely produce metamorphic porosity, there's not too many actually, and I've listed a few, the ones that I came across. And I want to spend the rest of the presentation to introduce you to a couple of experiments that take a closer look on some of these mechanisms. One of them is heterogeneous thermal expansion that we're going to look at. Heterogeneous which is essentially related to the thermal expansion behavior of different, which is material property, Similarly, the heterogeneous decompression or compression, which is related to the elastic properties of individual phases in a polymineralic rock. Melting, we probably skip that for today. Reactive volume change is obviously also, there's probably very few reactions that do not involve a volume change, and however transient that may be, it will involve a transient portion of porosity. Creep cavitation, we've shown you, dissolution, and hydraulic fracturing is obviously the most important, the probably most well investigated mechanism. Some of these mechanisms are fluid controlled, they wouldn't work without fluid being present. Others are quite grateful if there is a fluid around, and others don't care about a fluid at all. But what they all share is that they're all tied to changes in either temperature, pressure, or chemical potential. So wherever in a metamorphic setting we have a change in one of these parameters or more of them, we can actually assume that there could be the formation of porosity actually happening, which could affect metamorphic permeability, which could affect fluid-rock interaction in turn. Now, a question that arose for me from that, what are the time and spatial scales of all of these mechanisms? How important are they? If we kind of look at a piece of metamorphic rock, investigate its PTT evolution, how do we kind of fit all of that in? On what scales? How relevant are these? And are they related to particular pore geometries? We know that, particularly from a mechanical point of view, it does make a difference if there's a pore being formed that is like isometric or is a crack-shaped pore. Are they interacting? And what are the feedbacks between pore formation, permeability, fluid-rock interaction, the mechanical properties, and rock deformation? So that's a wide field that I'm not going to dive into. Before, I'm going to show you some results from four-dimensional experiments, time series experiments that we conducted. I want to show you a little bit more why synchrotron tomography is absolutely superior to any normal X-ray tomography. This is in fact, the results that I'm going to show you are only possible because we have these tools available. What you see here is the brilliance of a photon source versus the photon energy, and these two lines here are actually conventional X-ray sources as they're being used in desktop CT scanners. This is all kinds of complicated lines coming from the advanced photon source, which is kind of my experimental institution in Chicago that I frequently go to. I know that you have students who work more at ESRF. From Australia, it doesn't matter which way you go around. It's extremely far in either case, and we have connections to them. So the X-rays that we have available at the bending magnet that we're using, which is this blue line here, is by orders of magnitude brighter, and we have a much wider span of X-ray photon energy that we can use. So we have a lot more possibilities, and the most important ones are, so we have this much higher X-ray flux. We can choose essentially which energy we want to use or which bandwidth of energy we want to use. And if we decide to use what's called a pink beam, which is a bandwidth of energy that we use, we have such a high photon flux that we can acquire a three-dimensional data set in 0.2 seconds. And when I first heard this number, I got really excited, because what that means is that we can study processes as they happen. This really opens a new door to investigating fluid-rock interactions, all kind of other processes, really. And what is coming now, and I've been involved in a few kind of committees, is more and more high-energy X-ray beamlines, which means that we can study thicker samples, larger samples, and we can get away from this millimeter-sized stuff that I'm going to show you today. I want to spend a second also on this slide because there's the one aspect is the data generation. The other aspect is, of course, what do you do with this data? And anybody who has worked with X-ray tomography data will have faced the problem that you have to extract something else than just nice pictures out of these. And in Perth, I was really lucky because we had a very sophisticated infrastructure available, which allowed us to, we received both raw and reconstructed data from the advanced photon source, but we now have also the funding there to acquire a pretty state-of-the-art desktop scanner. And that was directly delivered into long-term data storage. We're talking here about a 40 data set is in the order of 3 terabytes of data, which takes, I don't know how long to analyze because I haven't finished to analyze one, but it's months and months and PhD students. But then it's all kind of running through a central workstation, which is relatively powerful, and we emphasize, and I cannot emphasize it enough, that it has to be the topmost graphic card that you can get to use that. It's not particularly important. What is important, though, is this dimension of the data sets that you can quantify. and that is a bottleneck of most of the commercial software packages, because they either need you to coarsen your data artificially, and that is why or just make smaller volumes, and that is why we have invested. We were lucky that we had this connection to a supercomputing institute, which allowed us to actually outsource all of the calculations onto 2 supercomputers. That has been shut down last week, but that is a replacement machine, which is more powerful. And obviously there's also a lot of software development that went in there. There's some commercial packages here, some open source stuff, but there's also, we had 2 postdocs who actually wrote code for us. Now let's look at a few more data. I want to skip this. This is a project that I've been involved in marginally. It's about partially molten rocks, but we can return to that in case there's particular interest. What I want to show you are 2 4D experiments that we did, and they're investigating porosity forming mechanisms in metamorphic, that should or might happen in metamorphic rocks. The first is one of the probably most prominent dehydration reactions, dehydration of gypsum. This reaction has been, or the system gypsum has been investigated since more than 100 years. There's a review paper from the construction industry side in 2003 or so, which states that we still haven't fully understood what's actually going on there. It's apparently simple. The important point that I want to get to is that if you form hemihydrate from gypsum, and that is relatively easily done, which is why I started working on this, that involves a volume change in the solid phase of minus 30%, but you release quite a lot of water with a slightly larger volume. So there's the net balance of this is that you have a plus 7% volume increase in a closed system. What is happening here is that potentially we should have, and that's the literature opinion too, we should have 2 mechanisms producing porosity. The one is obviously that volume change, but the other one is also hydraulic fracturing potentially, as we have this net difference in the volumes. We're going to see where we get. The other thing, if you study that literature, and it's quite abundant, if you dehydrate a polycrystalline gypsum sample, that alabaster, usually we use alabaster from Volterra in Italy, then there's different ideas of what the actual dehydration front looks like. Stratton has done a PhD on this topic, and she came up with this observation that she actually saw a very sharp front separating an area where gypsum is still stable and an area where hemihydrate has already formed. Wang and Wong have based a numerical simulation on a lot of experimental data, and they predict a porosity front to evolve very, very gradually. There's a very smooth blurred front over a very long distance, 20 millimeters in this case. So there is this very well-defined boundary here, and there's this very blurred boundary here, and it's also something that we wanted to test. The reason why we started dehydration is that it only involved, of these changes in the boundary conditions that I outlined earlier, pressure, temperature, and composition, it only involved the change in the temperature at first, and that is a parameter that is relatively easily accessible experimentally, because all the equipment that we introduce has to be X-ray transparent, because we need to count the photons on the other side, so if anything gets absorbed. So we need to design an X-ray transparent furnace, which is much easier than to design an X-ray transparent pressure cell. So this is our first prototype of the X-ray transparent furnace that we use. The sample is essentially sitting inside the furnace, and it can freely rotate, so the furnace is stationary. The window, it has 2 windows where the X-rays can pass through, and it essentially the sample rotates inside. We have then we didn't have the high-speed imaging available, so we had to stop the reaction, kind of shock freeze it, to be able to acquire a data set that does not change during data acquisition. Data acquisition then was about 25 minutes. So we had to, every hour here, we had to shock freeze the sample to 50 degrees Celsius, acquire a scan, heat it very rapidly again, have it running for another hour, and so on. Let's see some results. This is a vertical section through our sample cylinder. This is about 2.3 millimeters in diameter, roughly. The resolution of this scan is 1.3 microns voxel size, which doesn't actually say much about the spatial resolution, which is a bit coarser than that. What you see here is it's always the same section, but it's the same section at 4 different times. It's 4 quadrants. After 10 minutes, 70, and so on. What we can see here is the sample margin, and we very clearly see a very pronounced dehydration front, which is propagating inwards from the margins, and it takes more than 4 hours to reach the last bit of unreacted gypsum somewhere off-center here, and we'll come back to that. Of course, we quantified the advance of that reaction front. This is a horizontal section through that cylinder. You can see the position of the front at different points in time. You can also clearly see that it's a relatively irregular front. It does have, and it's, as I mentioned earlier, it's slightly off-center. So it's what we've quantified the advance here, and we showed it's a nonlinear fashion that this front propagates in. In fact, it slows down over time. Front progress is asymmetric, and we also found that with some idealism, the front progress can be fitted with a diffusion type equation yielding some diffusivity, which is not relevant right now, but which might be an interesting parameter to involve in upscaled continuum simulations later on. We also quantified the porosity increase, and this is a bit coarse here, but it does the porosity increase across the front, and that was quantified here. And first we do see that we actually reached the roughly predicted 30% porosity. It's kind of, this is a sampling effect here, this bump. But what it does show is that the porosity does not increase over a distance of 20 millimeters, which will be out there somewhere, but it increases over very narrow, about 200 microns. With our analytical tools, we know each pore by its name. We know where it sits, we know how big it is, what its surface looks like, what its orientation is, and so on. And the plots that I'm going to show you now are plots that, in this way, will not be possible to be created before we had this technique available, at least. What you see, this is pretty standard here still. This is the porosity evolution over time, and we quantified all of this data that I'm going to show you in the next couple of minutes in this volume out here, which is simply due to calculation time. The volume that we actually sample is about a cubic millimeter, which we considered statistically representative. You can see the front propagates through this volume, and it has finished doing so after 130 minutes, and that is also when the porosity kind of has its peak, and it kind of slightly decreases afterwards, which may be a sampling effect or actually have a physical meaning. I don't know. What we also can show here is, of course, the evolution of the sheer number of pores in that volume, and we see that there's actually, despite there's hardly any porosity in here, in the original material, there's a very large number of pores. So that must mean there's a very large number of very small pores, which are then is decreasing, and it's again then as soon as the front has left that particular sampling volume, is kind of stabilizing somewhere. This is a plot that shows you the pore size over time, the frequency of particular cumulative frequency here of particular pore sizes over time. And that is, you know these kind of diagrams from sedimentology, the grain size analysis that you usually get. So that's how you have to read them as well. What you see here, the magenta colored curve, is prior to heating. And as I've already told you that there must have been a large number of very small pores. And in fact, more than 95% of this porosity, the pre-existing porosity in this Volterra gypsum, is actually formed by pores that have a volume of less than 100 cubic microns. And that changes dramatically, and what you can actually take away from this diagram is essentially that after, say, 130 minutes, when the front has propagated through that volume, all the important part is actually formed by one pore, which is not one pore in the sense that we understand it as a geometrical feature. It's one interconnected cluster of pores. That is what the software returns at this stage, because we're not yet ready to distinguish stuff, pores, interconnected pores, and like separate individual of these things out. What we can also show, though, is, and that is now, all these analyses exclude the largest pore. They're just looking at specific samples of pores. These are the shapes, and we wanted to know, and that is relatively interesting, because if indeed hydraulic fracturing was a dominant pore-forming mechanism, then we would expect that most of the pores actually have aspect ratios that resemble a crack, which is generally given in the literature of around 0.1, so it's 10 times longer than it is wide. And that is a quantity that we can actually determine with our codes. And we've done that here for various pore sizes again. That's the pore volume in voxels. Sorry, it should be in cubic micron, but it's related. We can calculate one from the other. And that's the aspect ratio here. And any hydraulic fractures or any fracture-like features, whatever the mechanism was that formed this, as long as they have a shape of a fracture, would plot underneath this line. We see that the majority of the pores actually does not plot underneath this line, which indicates to us that it's probably not the dominant mechanism, hydraulic fracturing, and that does also not change over time. So that is about the end of the experiment. We see there's a slight shift in this curve, but it's on this cloud of points, but it's still indicative of the same thing. So there's very few pores that actually have these shapes. What you see here is stereo plots, and you're all familiar with stereo plots, of course. This is stereo plots which have as their kind of geographic reference the sample cylinder, and the vertical axis of the sample cylinder is plotting in the center. So what this shows us is kind of the orientation of the longest axis of these pores that we plotted up there, and so the orientation of these axes with respect to the sample. Interesting is that after 70 minutes we can see there's like a great circle forming here as a maxima here. In fact, these are 3 different size fractions plotted in each of these diagrams, but I won't go into any details, just they all kind of show the same pattern, and that is actually just reinforced after 310 minutes. Interesting for us was to observe that there's a similar pattern already recognizable, albeit there's of course much fewer pores, many fewer pores in here, but the same great circle is actually already present. And that kind of fitted together very nicely with this observation, which shows the diffusivity that we have determined as the kind of for the advance of the dehydration front as a function of orientation. And again, this is the same orientation, so the vertical axis is coming out perpendicular from the projection plane here, and we can see that the front is indeed propagating fastest in this direction, and that is essentially resembling something that we could not observe directly, but we did actually quantify shape anisotropies in Volterra Alabasta, and we did find that, of course, it's the gypsum crystallography that determines. It's not just the crystallography, but it's the shapes. It's a combination of both, actually, because the shape is tied to the crystallography anyway. But of course, the water is leaving the gypsum crystal in a particular direction parallel to the basal planes fastest, and that is where the advance of the reaction front is happening fastest. So if the front actually meets a bunch of crystals which are favorably oriented, it will be faster there than it will be perpendicular to that. I want to conclude with a short outlook on ongoing work, actually. That is a heating experiment that we did with westerly granite, and that was to investigate thermal damage in porosity formation during heating. You may wonder why we jumped on such popular things like gypsum dehydration and thermal expansion damage. The fact is surely that there's so much data already out there that we had a good benchmark to correlate our own observations with. So that's why we did the gypsum thing and also the westerly granite heating experiment. Westerly granite is kind of a standard granite, and I will show you that it's actually not a very good standard, in fact, because very strongly retrogradedly overprinted. Not correct grammar. Anyway, thermal expansion is a material property. We all know that. Many minerals like quartz show a very pronounced anisotropic thermal expansion behavior. And of course, as you can imagine, in a polyphase rock, differential thermal expansion, and it's also true for contraction, will lead to a heterogeneous stress distribution on the grain scale. And that may lead to failure in the formation of porosity. In fact, it does lead to failure in the formation of porosity, and it has been investigated in numerous experiments. And I've just picked one of them. Here about Hurd and Page, and Hurd and Page show how at various confining pressures, we want to only focus on that one up here, and the permeability and porosity evolves, and you can see that overheating of it to a temperature of about 300 degrees, the permeability increases by a factor of 2. We built a more sophisticated furnace for this experiment, and that was really challenging to do. Actually, this is the latest generation of that furnace. Sitting up here, it's then going to be lowered over the sample. The sample itself sits on this about 20 centimeter long ceramic pole. You can hardly see it. This is the whole detector array, and the blue bit out there is the high-speed imaging camera that we're now using. The challenge obviously was that data acquisition. In this case, we used I think a 3 seconds data acquisition time. So the sample rotated by 180 degrees in 3 seconds. But during this, we acquired about 1,500 radiographs in these 3 seconds, and of course they have to be geometrically very precise. So the rotation of this specimen on top of this whole array has to be precise within about a micron, or much less actually than a micron. And at 573 degrees, that proved to be quite a challenge, but we have actually extracted a good data set. What I'm going to show you here is an early experiment that only goes to about 400 degrees. Here we had a smaller sample diameter resulting in a high resolution, so we have a voxel size of 700 nanometer cube. Of course, we heat very slowly to avoid any temperature gradients, but we have tested that, and it's actually true. There's no temperature gradients, are not relevant in this experiment. This is the pre-existing porosity in westerly granite, and that quite surprised us. It's not a lot in terms of its volume fraction, but if you look at the pore density, then you find that there's about 1 million pores per cubic millimeter. And of course, from a mechanical point of view, they all play a role. And then there's the other issue, which is many of these are fluid inclusions, which of course also complicates the issue quite a bit if you start heating them to 400 degrees Celsius. The other thing is that if you look at the material in have a slightly closer look at that and do a little bit of analytical work on it, it's not too much to it, but you see that this is far from being a fresh granite. Has like a severe retrograde overprint. There's a lot of cations being exchanged, and so westerly granite is really not a material that we should use for rock deformation experiments, because there's a lot that affects it that we don't want in there. Nevertheless, there's all this data out there, and we had already started. And despite all this pre-existing porosity that you can already see in this, now this is again tomographic data, horizontal section. You can recognize the various minerals. This is the plagioclase in here. These are micas. This is a Kekelspar. I'm right, and this is quartz. You can get an idea that at 365 degrees, there's a lot of thermal damage that we have done to this sample and that we could quantify. And we did that. And as I said, we're still working on, currently we're working on a publication of this, so this is really work in progress. What you see here is a slightly, I apologize for this slightly complicated diagram. I'll guide you through it. It shows you 3 parameters evolving over temperature. The one is the porosity, and this is kind of an upper-lower bound estimate. So the porosity that we have observed in here is between these open and closed circles, and we see that it does indeed change. And we also see what has been described earlier in literature, that from about 300 degrees on, there is some change to what is a very boring evolution earlier. And that change has been attributed to either the rapid decrepitation of fluid inclusions of a particular kind, or actually Wang et al. have concluded that they've observed that, in fact, up to then, all the grain boundaries are open, and what is contributing to porosity here is intergranular fractures that form. It is also somewhat reflected in the number of pores, and so shall not be discussed in too great detail here. What is also quite interesting and easy to quantify from these experiments is really the thermal damage that we have done to this rock, which is affecting its use in other applications. Of course, what we can also use this data for, and I'm coming close to ending now, is to watch processes discretely, like damage discretely as it happens. What you see here is a 3-dimensional data set. It's about as thick as a thin section, and color-coded are different pore size fractions here. And you can, in the background, I have the attenuation image, the actual X-ray data. You can see cracks forming here, and you can see that there's a through-going large crack forming in that plagioclase over temperature, and then we can, of course, discretely characterize how that happened. What we plan to use this for somewhere in the far future is to do kind of in situ crack propagation studies, to learn more about fracture mechanics on the granular scale as a function, because we know many of the boundary conditions that are going on, and I'll come to that right now. The other use that we have for this data is, as many of you may know, that Klaus Regenauer is a pretty hardcore numerical geodynamicist, and so are all the other postdocs there. And of course, we want to do some numerical calculations around these experiments. And what we decided to do is to numerically reproduce the physical experiment. And we did that, and Christoph Schrank has presented that earlier this year in Vienna already, and I'm just repeating what he said. Here, this is really his work. We came up with this combined finite element, finite difference code, which reproduces that experiment. Here it's just a quarter of our, it's a 2D at this stage, quarter of our sample. It considers 4 mineral phases. All the physical properties that are relevant are very well calibrated and temperature dependent, and it does also include grain boundaries as contact surfaces. And they have, of course, properties in compression and in tension and so on. A very well calibrated experiment. And here, just for comparison, this is the linear thermal expansion coefficient as determined for westerly granite by Cooper and Simmons. There's 3 lines here, and these are the thermal expansion coefficients that we determined with our numerical experiment for the same temperature range. And you can see there's a very good correlation here. Now, this turned out to be a really powerful tool because we had this physical experiment that we could train the numerical experiment with, but then on in return, as a favor, the numerical experiment gave us a lot of information that we could never obtain from the physical experiment, such as, for example, magnitudes and orientations of the maximum principal stresses here at a given temperature. So if we observe something in our physical experiment, we can now go back to the numerical experiment and say, well, of course, because there's the stresses are reaching that and that level and so on. So this is a very powerful approach that I fancy very much. Final slide, just in time actually. A few conclusions. I hope that I could show you that pore formation is obviously deeply involved in synchromatic metamorphism in mid-crustal shear zones. That may not be anything that is new to you. That is an aspect that we can discuss if you want. Gypsum is stable until a dehydration front approaches to within 200 microns, which is quite interesting if you consider that the temperature equilibrates in that specimen within 3 or 4 seconds. So it should be at reaction conditions, yet it is still stable, and we are discussing in a current publication why that may be so. What I consider like really an achievement is that the link between the synchrotron X-ray tomography and numerical modeling proves to be really promising, and I personally consider that really as a future experimental environment, synchrotron doing in situ 4D studies. And one way to approach that is really to do X-ray, to come up with X-ray transparent experimental cells that allow us to study fluid rock interaction or any other process you want in situ in 4D with very high spatial and temporal resolutions. Thank you very much.